Thank you, Dr. Mahesh. Pleasure to be here. Thank you for the invitation. Hello, everyone. So I should say I am only the presenter here. This work has been very interdisciplinary and it has been very collaborative, done with multiple groups, including our main partners at the Bangalore BioCluster. So Professor Dasarathy has been, his lab has been doing most of the experiments here. So this project started at IIT Bombay. My own background is a mixture of computer science and molecular science, and so I have done some PCR in my PhD days. So I have always been, that fascination has been there with trying to do something connecting PCR and computer science and so on. So we had this idea. I had this idea early on in the pandemic that we could do something like this. A PhD student started work, another colleague joined in, and then we managed to get more collaborators, get this off the ground, and build something. So if you want to know more, this is the website, and the method is called Tapestry pooling. The problem we are trying to solve is, if you look at these pictures, maybe this brings a sense of longing in you. Students haven't gone to campuses. You probably haven't visited a place that looks like this for at least 6 months. Workers haven't had jobs in factories, and at least in many places, offices you've not been able to operate in this way. And the problem has been whether it's a government declared lockdown or whether it is some other local lockdown. There have been difficulties in keeping such places of work open through the day. It's not practical to expect people to sit in office wearing personal protective equipment through the day. So COVID has hit in this sort of double-barreled way. It's a health pandemic, but there has also been enormous economic distress, and we've been seeing lots of reports of this in the press from the very early days. And we have been asked to make this impossible trade-off. Do you want economic distress or do you want health distress? The truth is, we don't want either. We want a silver bullet. We want something that lies here, which will minimize economic distress, which will minimize health distress. Of course, vaccine could be one such silver bullet. Uh, it's getting closer, but we still don't know when it will be here. We don't know when it comes, how effective it will be, how much time it will take to prove its effectiveness, how long will it be effective, when do you need booster shots. It's a work in progress. There is something, though, that is available today that can get you somewhere here, and that is testing, especially if it can be made affordable, if it can be made scalable, if it can be made frequent. And we have seen the curves earlier on today from Dr. Pandey that, yeah, we have increased the amount of testing we have done, but we need more testing. Really, if we want to open up campuses, the kind of testing we need is something like this. We need 100 times more testing. Testing should cost 1% what it now costs. We don't want to test situations where many people are positive. That's the symptomatic case, that's the high prevalence case. I'm now talking about campuses where students have come back, they've all been tested 3 days back, they were all negative. I'm going to test them again today. So I expect about one person in 1,000 to be positive. Very low prevalence rate. I would like results very fast. I would like it to be very accurate. I would like it to be here now, within a month, ready to launch by January 2021 or something like that. Okay, so this is a wish list. And of course, the unsaid thing behind this is it should be practical. It should not just be pie in the sky. It should be scalable. It should not be limited to one campus somewhere in the world where somebody knows some magic trick. It should work across campuses. It should be something you are willing to trust. So it should be built on technology that is proven and that you can trust. Okay, so this seems like, okay, the best possible wish list you can make. But how close can we come to this? So we have this method called tapestry pooling. It's a method of pooling. It can give you at 1% prevalence, it can give you 20 results per test. It gives you results in a single round. So sample from every individual goes to multiple pools, not just one pool. And we are able to deconvolve and give you results, quantitative results in a single round. It's accurate, it is fast, you handle each sample only once, it's easy to use, and it's validated on more than 3,000 samples. It will save you kits, reagents, time, effort, a personal protective wear, and plastic wear. And there has been some recognition for our method. In Nature magazine, Dr. Soumya retweeted the article. American Mathematical Society has done a column on this. The SIAM, Society for Industrial and Applied Mathematics, has written about us. IEEE has written about us. So there has been a lot of attention to this method. and somewhat across disciplines. So both in medicine and in the pure sciences and in the community of mathematics and engineering, there has been some interest in the methods that we have come up with. Okay, so let me quickly tell you in a few slides what our method is. And of course, nobody needs to be told what PCR is, but I think it helps to look at PCR with fresh eyes. Okay, so with that point of view, let me think of the problem of testing as trying to find a needle in a haystack. You take a sample out of a person, there are a few copies of the virus, maybe 1,000 copies per ml or something like that, might be clinically relevant at the lower end. So there are a few needles in this haystack. So the problem of testing is there a needle in the haystack? So the silliest, stupidest method might be you go through this haystack blade by blade and ask, is this blade a needle? Is this blade a needle? And you go through till you find the needle, or till you find there are no needles. This is a very slow process, right? For the number of molecules, the amount of sample you would collect from a person, you're talking about Avogadro numbers. So you're talking about very large numbers, not a practical method. You could do a parallel search. So you could do something like, now k people are doing this search, and so the haystack divides into k parts, and each of them is going through the part of the haystack that they have to search. It's still linear, but you get a division by k over here. And you might imagine that doing sequencing is a bit like this, because essentially it's a sequential search but with many workers. So that's where the parallelism comes from. So here is a third method. Every blade of hay itself becomes a computer for you. It now asks, am I touching something made of steel? If the answer is no, nothing happens. If it is touching the needle, it turns into steel. And then every blade of hay that is touching that thing that now turned into steel turns into steel. So what you get is a chain reaction. And within a small amount of time, you're going to see the entire haystack turn silver in color. And this is the kind of thing that you might get in PCR or LAMP, any kind of exponential assay, and there aren't so many of them going around. They all seem to depend on this wonderful enzyme nature has given us called polymerase. And so PCR is something quite special. The thing to remember here is that the time for this to happen is very small. If there are n blades of hay, it's only logarithmic in the number of blades of hay. So if I want to search a larger haystack, the double the size, I need sort of time one more unit. That's all. One more sort of clock tick for double the size of the haystack. So I can keep doubling the haystack several times, and the search is very fast. So PCR is very effective in theory at searching very large haystacks. Now there are practical limitations in terms of the machines that exist in the lab for the size of PCR they can do and so on. But in principle, there is no such limitation. In principle, PCR is incredibly specific. You can trade off that specificity for doing really large volumes, and you can get away with it. Okay. PCR, of course, is a quantitative method if you keep track of how the fluorescence is increasing through time. So you have qPCR, which is answering a stronger question for you. How many needles are there in the haystack? Not only if there is one, but how many? And we can use this. We can make use of this. Okay, so what is the problem we are solving now in the current context? I want to say it is not the problem of diagnosis. It is not the problem of finding a needle in a haystack. It is this problem. Which haystacks have needles? We have so many people. We have 1,000 people in a campus. One of those people somewhere is going to have the coronavirus disease. One of these haystacks is going to have a needle. So I want to solve that problem. Which haystack has a needle? And the method to solve that problem need not be the same as the method you would take to test every haystack. You could do things like this. You could drive a tractor across row 4, collect half of the hay from each of these cells, pile them together into one big block of hay, and test this block of hay. If this block of hay is negative, then all these have no needle in them, right? All these people are negative, they can go home. This has been done at a large scale in multiple countries and done at some scale in India as well. It has led to substantial improvement in the amount of testing we can do. And one can think about when it can give false negatives. It depends on how much of the hay I manage to get into this pool. And one can ask, what is, if I get a substantial amount of hay into this pool, what is the probability that given there are k needles here, no needle gets into the pool? So this kind of math can be done. One can do it very finely and get a very clear understanding of false negatives and so on. And this works. So this is, one has a lot of control over how much pooling one can do. Yeah, again, we can say which haystacks have how many needles. This is a harder question to answer, but it turns out asking this harder question makes the problem easier to solve. And this is how. So in tapestry pooling, every haystack goes to three pools: vertical, horizontal, and diagonal. Each pool gives me a linear equation. And from these linear equations, I'm going to solve them simultaneously, assuming that most of the haystacks have no needles. And that's going to allow me to find out exactly which haystacks have needles and how much in a single round. So this is the method. This is the technique in sort of one slide. What this gives you is this. Single testing is going to give you the green line, pooling is going to give you the red line, and tapestry pooling is going to give you the blue line. So there isn't so much difference at somewhat higher prevalence, but once you go to prevalence below 1, this just shoots up. You're 10 times better off using tapestry pooling than using simple pooling, 100 times better off than using individual testing, because most haystacks are needle. Okay, you manage to do this without losing too much sensitivity, with a great decrease in cost. You manage to do this faster than simple pooling, because it's simple, because it's a single round. And we have some data to show. We have done validation trials with patient samples at INSTEM Bangalore and at CLIA lab in the US, and we have validated that pool sizes up to 31 and up to 60 can be made to work with various setups. We have built a web app that makes this all very easy to use for a lab, and we have worked out some flows that can be used for testing in the real world. So this could get you into a movie theater in half an hour with this kind of testing, and this could help you test a campus. With one round of PCR, you could test an entire campus. So I'll stop there and I'll hand it back to yeah.
Thank you, Dr. Manoj. Very, very interesting on how we use novel methods of computation and data analysis to actually improve the throughput of our testing for campus management